Niobium is one of the key constituents in alloy 718, the world's most widely used aerospace-grade superalloy. CBMM, the world's leading supplier of niobium and niobium technology, has recently developed a novel process to produce extra-low nitrogen raw materials for the production of a nitride-free alloy 718. This video explains why this is important and its potential impact on the aerospace industry. Nickel-based alloy 718 was originally developed as disc material for aircraft gas turbines, components which are exposed to high operating temperatures and stresses. In mechanical applications such as this, alloy 718's ability to resist fatigue failure and stress rupture over the anticipated life cycle of the component is critical. Lowering the amount of nitrogen in the alloy improves fatigue life, reduces the risk of failures, and increases the lifespan of the parts. Let's now find out from a leading expert why lowering the amount of nitrogen in these alloys is important.
I've been teaching at UBC for about 40 years and retired relatively recently to become an emeritus professor. And I've been concentrating since then on my work as a consultant with the engine builders, the superalloy manufacturers, and the specialist steel manufacturers in general. It came quite a few years ago in discussions with one of the engine builders who'd been making a substantial investigation into what caused premature failure in low cycle fatigue in 718. And what they'd found was that in order of importance, the most important factors were the presence of inclusions, which were always found on the fracture origin site. And on looking more closely at those results, it was clear that nitrides were a substantial part of that problem. The first thing that we did was to look more closely at exactly what were the inclusions that were being found on the fracture origins. And we found basically three factors were involved. The first factor was the presence of oxide inclusions, which are inevitable in the superalloys. And we found that they were being glued together by titanium nitrides. So if we looked at the inclusion collections in 3 dimensions, we found oxide particles which were stuck together in a 3-dimensional network by titanium nitrides. So our conclusion was that titanium nitrides were an important part in determining the behavior with respect to the oxide inclusions. The second factor that we found was that the primary carbides in 718, the niobium carbides, nucleate on titanium nitrides during their formation. That's why the industry calls them carbonitrides. They are in fact a composite particle. And we found that the larger titanium nitrides were nucleating the carbides, which caused all the problems with low cycle fatigue. So we concluded that on the basis of that, if we got rid of the titanium nitrides, then those problems ought to be greatly eased. The main factor is that we don't alter the fundamental properties of the alloy itself, but what we do is make the properties more predictable and reliable. So if we look at the LCF values that we obtain in high nitrogen alloys, normal nitrogen alloys, and low nitrogen alloys, what we see is that the LCF values are closed in. And for the low nitrogen content, the very low nitrogen content, what we find is a rather narrow dispersion of LCF values. In aerospace terms, that means the 3 sigma has been considerably reduced, which makes the property in engineering design much more predictable. The effect of nitrides on the carbide precipitation in 718 is also interesting and relevant. The carbides are normally produced by nucleation and growth during solidification. They are primary carbides. When there is titanium nitride present, the carbides grow on the nitrides and they have lots of time to grow into large carbides, which of course adversely affect the LCF life. When there are no titanium nitrides present, The carbide precipitation is delayed until the end of solidification, and we produce much smaller carbides. It's the same amount of carbide in principle, but it's distributed in quite a different way, and that positively affects the LCF life. In the context of investigations on LCF, the data which was obtained for the low nitrogen alloys was obtained by electron beam melting and refining 718. In the results that were obtained, it's quite clear that low nitrogen is a positive effect on the mechanical properties. However, the industry judged that this was not really a practical way to make that kind of alloy. Electron beam melting is too slow, too expensive, and too complicated to use on an industrial scale for this kind of superalloy. So although the idea was certainly available to the industry, and the industry recognizes the advantage of low nitrogen, there really was not a practical way to do this until this latest development. The implications of low nitrogen are not just applicable to Inconel 718. The alloy, of course, is the most widely used of the superalloys in the aerospace industry, and it's very important to improve its properties in this way. But at the same time, removing titanium nitrides has positive effects on the mechanical properties of many other alloys, both the alloys which contain niobium and even the single crystal alloys, in terms of reducing, for example, microporosity, reducing the problem of grain nucleation in the manufacture of single crystals. There are many other areas where low nitrogen becomes an important factor.
To enable the development of nitride-free alloy 718, CBMM has recently invested in developing very innovative patented technology and equipment to produce enhanced extra-low nitrogen raw materials and a test facility for the scale-up production of a superior end product. The facility is based in the company's Materials and Processing Research Center in Araxá, Brazil. This capability enables the production of nitride-free alloy 718 raw materials, nickel niobium and chromium niobium. It is also capable of producing electrodes for nitride-free 718 for vacuum arc remelting, allowing the production of real parts for in-field testing. This innovative vacuum induction melting furnace with atmospheric leak-free chambers is used to avoid nitrogen contamination from the atmosphere. The technology ensures nitrogen content is at a maximum of 5 parts per million, avoiding the precipitation of unwanted nitrides. With the nitrogen content of commercial grades typically ranging from 60 to 100 parts per million, this enables the ultimate development of nitride-free alloy 718. As an initial step, an aluminothermic reduction process is used by CBMM to produce the extra-low nitrogen nickel niobium and chromium niobium raw materials to be used in the alloy manufacture. In the vacuum induction melt furnace, the first stage is a carbon boil of the first raw materials added, nickel, iron and molybdenum, to extract the nitrogen. Then the extra-low nitrogen nickel niobium and chromium niobium are added to the melt. Followed by quality controls, temperature, then chemical analysis, followed by the addition of the final raw material, nickel magnesium. To complete the process, there are 2 casting routes: single cast electrodes and cast bars. This is one of the most important recent developments in the field of superalloys worldwide, demonstrating CBMM's investment in materials research and enhancing our knowledge of superalloys to the benefit of end users. This customized research and development and scale-up facility with a dedicated vacuum induction melt furnace has a 1.5-ton capacity. It can produce ingots big enough for the manufacture of actual components for material qualification. CBMM also has NADCAP accreditation to meet the most stringent requirements of the aerospace industry. Working in partnership with the supply chain, advancing the properties of alloy 718 will bring new levels of quality, safety and reliability. enhancing engine design and improved operating efficiencies and associated reductions in emissions, and further adding value in other sectors, such as power generation and oil and gas exploration and production.